It's been a while. Welcome back to my channel again. My name is Mr. Chai. Today we're going to talk about vector product, or sometimes it's known as a cross product here, right? So here I'm going to give you a very simple and easy to use methods to follow whenever you perform a vector product or cross product here. Right? Now, to ease our understanding, I'm going to use an example here. Right now, we're going to let's assume that you have a vector A, which is given by, I have already written down that. Just let me check that number here, 0, and then vector B as let me see whether I remember the number, 4, 1, -1. Okay. Right. Now, how do we perform the vector products? So vector product, notation-wise, we write it down as a cross. Is a cross product. Okay. So this is the notations for vector product. And then the way we perform vector products by definition is given by this definition here, ijk, and then we're going to fill up all these component for vector A, which is this, and then a component for vector B. All right. Now this symbol basically refer to the same symbol that we use to evaluate the determinant of a matrix. Right? Now, just for a recap, for a simple determinant of A, B, and C, D. So if you wish to find the determinant for this matrix, it is given by A here. Okay, so the process would be A multiplied with D. So we have AD, and then after that subtract with B multiplied with C. Right. Now that's how we perform the discriminant methods here. Right. Now we're going to extend this simple idea onto three-dimensional determinant. Now to do that, first of all, we're going to start from the I component. Right. Now one way we can do it is by crossing out. Right. Crossing out the I component like this. For instance, you can cover this. So if you cross out these two column and row that basically cancel off the I, you can see that we have, this is what we can see here, this region. And then this area contain -3, 0, 1, and -1. There's a special name for this. If you are interested to know about this, this is called the cofactor. Cofactor of component I in this case. And then we get to perform the determinant for this cofactor. So based on the formula for determinant is AD minus BC here. So the first vector product would give us, all we need to do is compute the determinant. So determinant will be -3, right? -3 multiplied with -1 minus of 1 times 0 here, and then all this is the I component. All right. Okay, now that's how we do it. Now we get to repeat the same process for the I component. So all we need to do is draw a horizontal line and a vertical line that crosses the J. Right. Now in this case, we will be able to pick up the cofactor here, which consists of 2, 4 and 0, -1. And then all we need to do is repeat the same process again with a bit of difference as compared to before. Here, the first computations would you have to include a negative sign here. So for the first computations of the determinant for component I is a positive determinant. Then the second component for J is a negative determinant. So we will write down negative and then obtain the determinant for this component J. That will be 2 multiplied by 1 and then minus of 4 multiplied with 0. And then that will give us J. Alright. Now always remember the sign here is alternating. We start off from positive and then negative, and then of course lastly you expect to get a positive again. Alright. We're going to repeat that for the cofactor for component K here. Right, now by repeating the same process, I'm going to draw a line here and then a vertical line to cross out the K. In this case, what we can see is the discriminant that is corresponding to component K. And then all we need to do is write down, because the sign is alternating, so the last one will be positive. We have 2 times 1 minus of negative 3 multiplied by 4. And then that will be our vector products. And then to simplify all this, we have 3i. And then this one here, we have negative 2 become positive. And then lastly, we have a 12 of 14. So that will be a 14k here. Alright. Now it's either you can write it down in the Cartesian form, or you can write it down in a more modern notation, which is 3 to 14. Alright. Now there you have it. This is a very simple introductions to a vector product. Right? So as long as you perform a vector or cross product, this is the rules that you need to follow. And then don't forget, the sign is always alternating. You start off by a positive determinant for component I, and then negative component of the determinant for J, and then lastly we alternate the sign again to positive determinant of the component K here, and then that conclude the vector products of this A and B. Now the significance of vector product is basically to find a vector that is perpendicular to the plane that contain A and B. Right? Now next part I'm going to explain a bit as to why we need the vector A and B. So take for instance you have vector A here. So let's assume that this is vector A. I think this one will be easier. Let's assume that this is vector A, this is vector B here. Right. Now the geometrical significance of vector product is if we cross A with B, what we have is actually a vector, is yet another vector that is perpendicular to the plane that contain vector A and B here. So take for instance, in this case I'll write down this is A cross B, and then the plane is somewhere here. So let's assume that this is found on the plane. Okay. Alright, so we are making assumptions that as long as vector A and B are found on the plane, on any plane at all, and then the cross product between A and B would produce a vector that is normal. Sometimes we use the term normal to the plane or perpendicular to both the vector A and B. So that is 90 degrees. So generally, the purpose of performing vector product is to obtain a normal to both the vector A and B. Okay. So I hope that is useful. you must know the significance, and then the technical process. How do we produce its vector product here? Okay. Now, of course, there are some other methods that you can use to perform the vector products or cross product. Right? Now, rather than using this very traditional method, I'm going to show you another one if you are interested to use it. Okay, so let me erase all this. Perform the vector product is as follow. Instead of using I and j and k, we can write it down like this. So we can perform the vector product directly without indicating the I, j, k. Right. Now the way we are going to perform this is exactly the same like what we did. Now because the I component refer to the first row, so we're going to ignore the first row, and then we are going to concentrate on this particular cofactor. So this one will be our cofactor. All we need to do is write down the first evaluations of this determinant, -3, 1, -1, and 0 here. Now -3 multiplied with this, I'm going to write that down, minus of 0 with a 1. Okay, now that's our first component. Next, we'll follow the same rule here. We're going to highlight the determinant for the j component. So the j component is the middle row. All you need to do is look at this cofactor here. So the cofactor we are looking at is 2, 4, 0, and -1. And then we're going to repeat the same calculations for its determinant. Now that will be 2, -1, minus of 0 with a 4. Now the only thing you need to remember is the sign. The sign for the second determinant is a negative here. So I'm going to put a negative down here. The sign for the first one is positive. Now, even though you don't really need to indicate that. Now that will be something like this, right? So I hope that's clear. I will show you the next. Last determinant, the last section of determinant, we are looking at the k component. Now for that, we're going to highlight this cofactor here, which is 2, 4, -3, and 1 here, right? And then we're going to repeat the same process. This time the sign will be positive again. So all we need to do is evaluate these numbers or this determinant. Right. And then I'm going to simplify these calculations now. That would actually give me a 3, and then that would be, did I get that correct? Just let me check. The second one is -2, so it's +2, and then the last one will be 12 or 14. And then there you have it. That is the vector products between A and B. And then I'd like to reiterate again, the significance of this vector product is to obtain a perpendicular vector to both vector A and B. So I'm going to redraw it here again, just to recap. So we have a vector A, and then we have a vector B, and then the cross product between vector A and B would produce a vector that is perpendicular to both vector A and B here, and this is given as A cross B, right? So I hope that has been useful information for all of you. Right, now the next part I'm going to show you some of the questions that make use of vector products, right, in the following section here. Right, I'll see you again. This is our first vector problems. Right, let's read through. So here you are given a line L has this vector equations given as such, where A is a constant. The plane P has an equation as given x plus 2y plus 2z equal to a 6. Now we need to find the value or values of A in each of the following cases. Right, now the first case, the line L is parallel to the plane P. Right. Now for any vector problem, if we can sketch out the diagram, right? We can sketch out a diagram to represent the graphical representation of the line and the plane, then that will be a bit helpful to our analysis. So let's try it out for number 1. So we have a plane here. Yeah, you can call the plane any name you like. So in this case, they have already given the name for this plane, plane P. And then usually this plane would have a normal to its plane itself. Okay, that sounds ridiculous. Right. So there is a normal to the plane. I will label this as MP. So this is a normal to plane P, and then this normal can be obtained from its Cartesian equation here. That is given as the coefficients for the x, y, z. That will be 1, 2, 2. Now that will be the normal to the plane itself. So it's normal here, right? And then next way is the line. So the line is given as this equation here. The line also has a direction. So here it says that the line is parallel to plane. Now we're going to draw a line there. It can be any line you like to imagine. So let's assume that the line is parallel. Okay. So this line is parallel to, so it's parallel to this plane here. So the line is parallel to the plane. Right? Now, because this is a vector, so you can sort of represent this vector on any position in space as you like, because the reference point where it started from is not that important in this case. So instead of drawing it this way, you can also present it some way here. Okay, I can draw another line which actually represent the same vector here, the same vector, but in this case I purposely put it nearer. Alright, so nearer to the plane, so it's easier for us to see what we are looking at. So this line here, this line 1, line L is given as 1, 1, 1. Is it 1, 1, 1? Yeah, correct. So plus A 2, 1 here. So this line has passing through this position vector 1, 1, 1, and then it has these directions here. So this second section represent the direction. You can also put this onto the plane itself, because this is a vector, so it can be placed in any direction in free space. So for that, I'm going to place it nearer to the plane. It's easier for us to analyze in this case. So the line L is parallel to the plane. Now in this case it's parallel to the plane. Now because line L is parallel to the plane itself, and then we knew about this normal vector, because the normal is perpendicular to the plane, and then since the plane is parallel to the line, then therefore the direction of the line, the directions of the line in this case is given as A 2, 1. So the direction of the line and the normal must be perpendicular to each other here. So I'm going to draw that here. So that must be 90 degrees to each other. Now in this case, we're going to use scalar product, right? Since they are 90 degrees to each other. So number 1, since they are 90 degrees to each other, then we can conclude that the scalar product between the normal of plane P and the directional vector for line L must be equal to a 0, because cosine theta is equal to 0. I'm just going to write down the formula to work out the scalar products one more time. So just as a for reference in this case, if we use A dot B, then that will give us A magnitude B cosine theta, where theta is an angle between the both of this vector A and B. Now, knowing that they are 90 degrees to each other, the scalar product between these two vector must be equal to 0. Right. All we need to do is just substitute this in here. And then that will yield A plus 4. 2 times 2 is 4, and then 2 times 1 is a 2. This whole result must be equal to 0. Therefore, we can obtain our A to be -6 here. Right. So that is our first value of A that satisfies these conditions. Right. Now I hope that is clear for number 1. Okay. Now for second one, let's read through the second one. The line L intersect the line passing through the point with position vector, both of these, right? So the line L intersect with another line that passes through these two positions vector, right? We can look at how to analyze that. Again, my advice is to sketch out a diagram to represent this. All right. Now number 2, we're going to sketch out a diagram to represent this scenario. So we have let's call this point A and B, for instance. You have point A and or position vector A and B. A is given as you can call this as 1, 1, -1 if you like. You can name it anyhow you like. So B is 3, 2, 1 here, and then there is a line that passes through position vector A and B. And then this line intersect with the line L that is given here. So this line L here has a vector equations given as 1, 1, 1, 0, 1 plus lambda A 2, 1 here. Now the first step is to work out the equations for a line that passes through A, B here. Now first of all, we're going to get the direction. The directions of this line. Let's call this line line number 2. This one we'll call it line number 1. It's easier to relate. So we have to work out the directions for line 2. So directions of line 2. Now we're going to work out the directions for line 2 here. And before that, we're going to evaluate the vector AB first. Vector AB is given by OB subtracted with OA. So we have our position vector here, which is 3, 2, 1. And then subtract out with 1, 1, -1. And then that will give us a 2, a 1, and a 2. Okay. And then next, we are going to obtain the unit vector as a recap also. Unit vector will be given by 1 over the magnitude of this vector. Now the magnitude of this vector is basically a 3, and then there you go. Now there will be the unit vector pointing in the same directions as line passing through AB. Okay. Now that will be this one will be our direction, our directions vector for this line L2. So this is L2. Right. Okay. And then we are almost done. To obtain the equation, the line equations for L2. So the line equation for L2, we can actually label that as R2. Now it must passes through a point. You can choose any point you like here because this line passes through A or B. So either way, you have to choose a point where it passes through. For instance, in this case, I can choose 1, 1, -1 instead. And then following by the directions of this line. Now the directions of this line, you can actually write 1/3, 2, 1, 2 here. Okay, but you do notice that the mu is a scalar quantity, and then 1/3 is also a scalar. Therefore, this whole scalar can be written as or combined as a single scalar. So here I'll just write it down as like for instance you write as a t 2, 1, 2 as one scale. Now there you go, there's the equations for line number 2. And then they do intersect at certain positions here. Let's label that positions where they intersect as a P. Alright. Now before we work out the positions where they intersect, I'm going to rewrite all the vector for L1 and L2 once again. Then we're going to solve these two vector equations simultaneously. Two vector equations that represent line L1 and L2 here, right? I have written that, okay, as such, and then they meet at the point P, for instance, or point Q, however you like to label them. Now, because they meet at one point, we're going to solve this simultaneously. So for that, we can rewrite these vector equations as such. So we can rewrite this again as 1 plus lambda a, 1 plus 2 lambda, and then 1 plus lambda. And then the second part we can also rewrite as 2t, 1 plus t, and then -1 plus 2t. Now because they are meeting, therefore we say that vector 1 must be the same as vector 2. And then all we need to do is equate both of these. Then that will give us 1 plus lambda a must be equal to 1 plus 2t. That will yield lambda a equal to 2t. That will be our first equation. We can't do much here. Then we're going to compare the second component, which is 1 plus 2 lambda must be the same as 1 plus t here. Then we found that 2 lambda is actually equal to a t. Now that will be our second equations. From here it's quite obvious. You can solve equation 1 and 2, and then doing so we will be able to obtain lambda, a. You will be able to obtain a directly from here. So take for instance in this case, let me see, there will be a 4 lambda, therefore a must be equal to 4. Okay. And then the last part you can check. The last part is for checking. So for checking, I will write down here to check whether our simultaneous equations is correct. So for checking, we can use 1 plus lambda must be equal to -1 plus 2t. And then knowing this as 2 plus lambda equal to 2t. Now knowing that a is 4, okay, a is a 4, we can actually substitute back here. So if a is a 4, therefore we have t equal to 2 lambda here, and then we can also solve this these two sections here. So we can label this as equations number 3, and then we can solve this. Now let's try to solve it here between equations 2 and 3. Now solving that would give me a lambda equal to 2/3. So lambda is 2/3, and therefore we will be able to obtain t equal to 4/3. And then by putting back all this value, just to check whether it tally, then we will be very sure that yes, all these values should be correct. Okay, so once you are happy with all this result, a, we have already answered the question here. We obtained the a. Now we have already obtain the lambda and t. If you are interested to work out the position where they meet, yes, by all means, all you need to do is just substitute the lambda or the t back to either one of this equation to obtain the position vector where they are meeting each other. Okay, so I hope that is clear for second question. Okay, now the diagram, as usual, we must draw the diagram. Here I have already prepared the diagram. You can see that there is a line that is intersecting with the plane. It may or may not intersect with the plane. I'm just drawing that in such a way that it's easier for us to analyze the angle between the line and the plane. Right? There are cases whereby the lines may not be intersecting with the plane. We can still work out its angle that the line make with the plane itself. Right? So here, before we can work out the angle between the line and the plane, which is given by theta here, it has already stated here the theta is equal to this. Right? Now, this is given theta is equal to tangent inverse 2. Now that is what is given here, and then from here we know that tangent theta must be equal to 2, and then we know that this is a acute angle. Right? This is an acute angle, and then we can also work out some other trigonometry ratio from the tangent itself, knowing that theta is acute. So here I'm going to draw a right angled triangle, which is 2, 1 here. Then there will be a set phi. So from here we can indirectly work out the sine. So I'm going to write down all the ratios that we need. So sine is 2 over set phi, or we can also have cosine, which is 1 over set phi. Yeah, it might become handy. Right? So first step, we're going to work out the cosine using the scalar products formula. The scalar product formula state that cosine alpha must be the same as the product between these two, and then this one is given by the directions of the line L. So direction of the line L is A21. Now that will be directions over its magnitude. Okay, so there you have it. And then from here, all you need to do is multiply this with its directions. Yeah, I forgot to label the directions for the plane. This is 1, 2, 2. Okay, so that will be, if you work out the scalar product, we will get a plus a 4 plus a 2 over 3 here, and then that will be a square 5 square root. Okay. But the angle that we are interested to get to represent the angle between the line and the plane is theta. We know that theta is 90 degrees, subtract off with alpha. Okay. Therefore, in this case, cos, we're going to apply sine theta is the same as sine pi over 2 minus its complementary angle in this case. And then using one of the identity, we know that this is the same as cosine alpha. And then cosine alpha is given by this. So therefore, we can say that a plus 6 over 3 a square plus 5 square root must be the same as the sine theta. So sine theta is 2 over sec phi here. And then from here, all you need to do is just solve for a in this case. Right? So let's give that a try. That would be a 5a plus, oops, I think I did something wrong here. Just let me clean this up. That shouldn't be the case. It should be 5a plus 6 square, right? So in this case, it'll be 4936a squared plus 5. Okay, that's what we have. So from here we have a squared plus 12a plus 36. Okay, now here we notice that 536 is can be cancelled out, and then all we have is basically 36a squared and 5a squared. That would yield let me see, that will be 31a squared. 31a squared, and then what else we have? We have minus 60a, and then finally minus yeah, that's it. So finally it's equal to 0 here. And then from here we will be able to obtain a result which is equal to a is either equal to 0, or it could be equal to 60 over 31. Alright, now there you have it. These are the two possible values for a that satisfy these conditions here. Right. Now I hope that is useful for this example here. We're going to continue on to the second questions now. Alright, now I think before we start, I have already prepared a diagram here that represent the setting for this problem. So here we are given a line L has this equation. So this line L is indicated here. Just let me label that. So this is line L. It has an equations 1, 2, negative 1 plus its direction here. So I will label this as R equal to 1, 2, negative 1 plus lambda 3, negative 2, and 2. Alright. Now that will be the vector equations that represent the line L here. And then we also have the plane P. Okay, so plane P, this is plane P. So plane P has these equations here. So plane P, I can write down the plane equations in the form of vector. I can write as 2, 3, negative 5 equal to 18. Now that will be the plane equations for P. So the first question, just read through the first question. Find the position vector of the point or intersections between L and P. So that will be somewhere here. This is where they intersect. And then let's read on before we answer the rest. Find the acute angle between L and P. Find the acute angle between L and P. So this is P, this is L. So the acute angle between L and P, that will be represented by this angle here, theta. We will work with that shortly. Right? So let's look at number 1. Oh yeah, by the way, before I move on to number 1, we can read through number 3 first. Second plane Q is perpendicular to the plane P and contain line L. Find the equations of the plane Q here. So based on the diagram here, it is quite obvious the Q is somewhere here. This is plane Q. And then plane P and Q is 90 degree to each other. So you can see that this is actually 90 degree to each other, right? And then the plane Q contain the line L itself. What will be the equations for plane Q? Right? We're going to work with that in a while. Let's look at number 1. Find the position vector of the point intersections between L and the plane P. Now I'm going to rewrite the equations for L, which is given as 1, 2, 1. Is it 1, 2, 1? 1, 2, negative 1. Yeah. All right. Now we can write in its compressed form, that is 3 lambda 2 minus 2 lambda negative 1 plus 2 lambda. Okay, just let me observe it, check that carefully in case I make mistake here. Okay. Now that will be the line equation. And then because this line intersect with the plane, therefore we have to solve the simultaneous equations between the line and the plane itself. And then these sections here represent the x component, this one is a y component, this one represents the z component. All you need to do is, before you do anything, the plane equations for P is given as in its Cartesian form. All we need to do is just substitute its x component. Oops, I think I wrote down wrongly. It's supposed to be a lambda plus 3y, so the y is here. And then after that, minus 5z. Right, now that's 5z equal to 18. Okay, now let me try to finish that. 6 lambda, 6 lambda, and then there's a 5, there's a 10 lambda equal to 18. Okay, so here I can see that I have 10 lambda, I have 8, 13, that is a 5, okay, so there's a 5, therefore the lambda would be, let me see, what do I have here, 8, 13, so negative 5, or negative 5 over the other side there, so this one will be negative 0.5. So the lambda will be negative 0.5 in this case. And then knowing that the lambda is negative 0.5, then we should be able to figure out the point intersections between the line and the plane. Therefore, the position vector or point of intersection is given by, I will just call that point B. Okay, let's call that point B. Point B. When I say point B, I write down A. Okay, so point B, let's call this point B here, will be given as, all we need to do is just substitute this one back here. Now that will be a negative 1.5, negative 0.5. And then the second one is a 1, with a 3. And then the last one is a negative 1, negative 2. Okay, now that will be the point intersections between the line and the plane P. Right? Now I hope that is clear. We're going to move on to the next. Second part. Find the acute angle between line L and plane P here. That is indicated by this theta here. And then we also know that there's a normal to plane P, which is given by this vector here. So the normal is given by, the normal to P is given by 2, 3, negative 5. Now as you can see, this normal is quite far from this plane here, so it's rather difficult to actually visualize what is the angle between this vector, this normal vector, and the directions of this line here. Now, therefore, it's always easier to transport this. So we can actually redraw this onto the plane here for ease of analysis. Now, in this case, I will draw this as a vector that is parallel to this normal vector. So I can also call that vector P here, just for the ease of calculation. Now we know that the directions of line L is given by this part here. This is the directions for line L. And then first step, like the questions before, all you need to do is work out the angle between the directions of line L and the normal vector here. So we're going to work out the angle between the two vectors. Cos alpha, based on the diagram, is given by NP dot with NL Okay, and then that would be, let me see what we have here. We have 3 to negative 5 and 3 negative 2 2 over the magnitude itself. So let me see here. 429 38, so 38, and then here you have like 8 9 17. Is it 8 9 17? 8 and 9 17, yes, correct, right? Then I'm going to simplify this a bit. So we have this is a 6, this is 6 is done, so negative 10 over 38 square root 17 here. Now from the calculator itself, we should be able to work out the alpha. Okay? So just let me. The is indicated as 66.83 degree. Okay, 66.83 degree. But the angle between the line, the acute angle between the line and the plane is given as theta. So therefore, the angle, acute angle between L and P is given as theta, and then that is 90 degree minus of 66.8 83 degree. Just let me clean that up. All right. Now that would actually give us 23.17 degree. Right. Now that will be the angle between the line and the plane itself. I hope that is clear for second question. We're going to move on to third question. We need to find the equations for the plane Q that is perpendicular to plane P, and then that contain the line L as indicated in the diagram itself. So we need to find the equations in its Cartesian form. Now what we need to obtain for this plane equations Q is its normal. Now we need to work out its normal in this case. In order to work out the normal to the plane Q, now I'm going to clean up a bit here so that we can see what we are looking at here. We don't need this anymore. Okay. Now we will still need that line, that normal that is parallel here. Okay, we still need this. Just let me label that. This is NP. Now we still need this normal to plane P. So because normal to plane P is sort of on the same plane, as the line L in this case. We're going to make use of this vector, the normal vector, and the directions for line L, and then to work out the normal. So if you place this normal together with the directions of L, we can apply the cross product or vector product to obtain the normal vector to plane Q. Just let me draw the vector here. So we will be able to work out. Oops, I'm using the wrong tool here. Just let me clear that up. Then that will be something like this. Okay. Now this will be the normal to plane Q that we are interested to obtain here. How do we obtain the normal to plane Q? Now normal to plane Q should be obtained from the cross product or vector product between the directions of line L and the normal to plane P here. And then that would actually give us NP cross product or vector product with the directions vector of line L. And then from here, our NP is given as 2, 3, -5. So we need to cross that with the directional vector here, which is 3, -2, 2. Right. Now here I'm going to use a more direct approach here instead of using IJK. Okay. That will be a 6 minus a 10, -4. And then the second one will be a 4 with 15, 19, but it's a -19 here. And then lastly, I will have a -10, is it? -4 and a 9, -13. -4 minus 9. -4, -9, -13. So -13. Alright, now that will be the normal to plane Q. Sometimes you can actually drop the negative sign here if you like. Right? We're going to finalize that in a while. Right, now for any plane equations, usually we use a more simple formula to work out the equations for the plane, which is given as R dot with the normal to the plane itself equal to any point on the plane, dot with its directions. Now we know that in this case there is a point on the plane there, which we have actually worked out. Right? It can be any point. You can use this point that we have worked out, or you can use this particular point here. Right? So any point will do, as long as it's on the plane itself. Right? So example, in this case, I'm going to choose this as our point. So therefore, it will look something like this: R dot with instead of taking negative all the way, I can just drop the negative because that is the same directions that we are looking at. And then from here, we can choose any point on the plane itself. Maybe the point of intersections that we have worked out, or it can be any point here. For me, I will rather take this because in the exam I have no idea whether I have obtained my intersections correctly. So it's safer to use what is given here. -1 dot with the directions vector, which is 4, 19, and 13. So from here, all I need to do is work out this scalar product. So there is a 4 to the 8, 4 to the 8, 42 there. So 42, I will get a 29. So that will be a 29. You can leave it in the vector form, but the question wants us to leave it in terms of Cartesian format. So therefore, in terms of Cartesian format, it will be 4x plus 19y plus 13. Z must be equal to the 29. Then that will be the Cartesian form that represent the plane Q. I hope that is clear. Right? I'll see you in the next question short. Right? Now I've already drawn the diagram here. Now based on this question here, we have plane P given as that vector equations in the Cartesian form, and then plane Q, here plane Q contain a point A, and then both these plane P and Q are parallel to each other. So the first question is find the equations for Q, giving your answer in the form of ax plus bx plus cz equal to d there. So both of these are parallel to each other. It consists of a position vector A here, which is given as 1, 4, 2. How do we work out the equations for plane Q here? Right, now we know that equations for plane Q is parallel to plane P. Therefore, both of them share the same normal. So the normal vector is given by this. Therefore, we can conclude the first answer quite easily. We say that plane Q will have these vector equations R dot with the directions, the normal scalar product with, so R's scalar product with the normal to the plane P and Q. Both the plane is having the same norm, which is 2, -3, 6. And then you must choose positions on the plane itself, which is given as such, 4, 2. And then also scalar product with the directions, which is this. That will be a 2, a -10, and then 12, that will be a 2 here. Therefore, the Cartesian's equations for the plane Q is given as 2x minus 3y plus 6z must be equal to a 2. Let me see. Yeah, correct. So that's number 1. We are done. It's quite a direct question here. Number 2, calculate the perpendicular distance between P and Q. So since P and Q is parallel to each other, we just need to work out its perpendicular distance as shown here. So the perpendicular distance must be the distance between this section here, right, D. Now the proper way to work this out is by making use of the unit vector in the directions of the normal. So we're going to work out the unit vector in the directions of the normal here. Okay, let me see. 36, 4, 40, 49. So that will be a 1, 7, 2, -3, 6. Now that will be the unit vector in the directions of the normal. Okay. And then we know that the A is located here. Therefore, if there is another position B here, then we will know for sure OB must be OA. It must walk from A here and then travel D unit up, D unit in the directions of the unit vector. So that will be a D unit up multiplied with the unit vector. So this is like how many units you need to walk from A here. So from here we're going to solve this. We know OA is given as 4, 2 plus a D directions factor here, which is 1, 7, 2, -3, 6 here. Okay, so that's how it looked like. And then you can actually combine this properly. So if we combine that, that will be 1 plus 2D over 7. I have 4 minus 3D over 7. And then finally I have 2 minus, sorry, 2 minus 2 plus 6D over 7. Let me see whether I got it right. Yep. And then furthermore, we know that position or the point B is located on the plane P, which is given by this equation here. Therefore, all the components for the position vector OB must satisfy x, y, z here, must satisfy these plane equations here. Okay, now I'm going to erase off the top part. We are going to proceed on with the final calculations here. So for number 2, continuations from here, all you need to do is substitute all its component x, y, z into the plane equation. Now that will be 1 plus 2d over 7 minus 3y plus 6z, and then that should yield 16. Let's give it a try here. We have 2 plus 4d over 7 minus 12 plus 9d over 7 plus 12 plus 36d over 7 equal to 16 here. And then we're going to simplify this equation here. You have 14 on the other side, 1349. Okay, let me see what we have here. 14 this side. We have 49, so 7D equal to 14, and then that would yield a D equal to 2 unit. Now, since D represents the perpendicular distance between plane P and Q, therefore we know that the perpendicular distance between P and Q must be given as 2 units long. So I hope that is clear for second question. Let's move on to the third one. Question, I have add on the extra diagram here. It is given that the line L is parallel to plane P. So line L is parallel to plane P, and it's also parallel to the plane pi here. So I label the plane pi as given here. This is the plane pi given as x minus 2y plus 2z equal to 5 here. And then this plane must have a normal that's pointing in this direction here. Now, given that L passes through the origin, find a vector equations for L here. Now, as you can see, all these vectors are kind of in the three-dimensional space, so it's very hard for us to visualize how to actually obtain the equations for the line. So the best way is we can transform. We're going to transform here. So I can transform this normal to the plane pi onto this line here. So I can label that as n pi. And then I can also transform that line, the green line L there, onto this line here, so that it's easier for you to see. So that is line L. It's always good to put them three together so that we can see what types of vector operations that we can perform. Now we are interested to find out the directions for this line. That is this direction. So you can see that from here is actually involve the vector product between this normal and the normal to the plane pi here, because the vector product of these two would yield the normal, or we yield the directions to line L in this case. I'm going to write that down, number 3. Number 3 will be given as, the first step is to figure out the directions for the line L. So the direction for line L can be obtained by using a vector products between the normal and the normal to the plane pi here, as shown in the diagram. So from here we have 2, -3, 6 cross with the normal here. The normal for this plane pi is given as 1, -2, 2. And then we're going to simplify this. Okay, just let me try out here. So -6, that's a -6. So it's a 6. Okay, first one is a 6. Then the second one would be a 4. It's a -2, so it's a 2. And then the last one will be a -4 plus a 3, -4. And then there you have it. There's the directions for line L. Because we are given that this line L passes through the origin, therefore the equations for line L now will be given as, all we need to do is just write down L, it passes through the origin, and okay, and in this case it has this direction, 6 to -1. Yeah. Or for simplification, you can actually write it down as such. Right. And then there you have it. That will be the equations for line L in its vector form. So I hope that has been useful to your understanding. Now, vector require a lots of graphical representations before you can actually analyze it correctly. Okay. We're going to attempt the last questions before we end for today's. Here, based on the diagram that I have drawn, we are given a line L that has these equations here, vector equations. It passes through 4, 2, -1, and then in these directions here, 2, -1, -2. And then there's also another plane pi. I just label it as plane pi. This plane pi contain the line L just now. And then this plane pi has equations given as such is 2x plus by plus c equal to plus cz equal to 1 here. So our problem will be to find the value for values of b and c. Okay. Now that's the first part. The second part is we have a point P that has a certain position vector 2, 4. Show that the perpendicular distance from that point onto the line is given as cert phi. So let's assume that there is a point A here. Oh, sorry, it's point P, not A. So there's a point P here that has a position vector as 2, 0, 4. And then we are interested to find out or to show that the perpendicular distance from this point to the line is given as such. So the D is equal to cert phi. That's what we are trying to prove for the second part, right? Okay, we will come to that shortly. So let's clear this up first. All right. Now let's look at number 1. Now line L is lies in the plane with the equations there. So since it's lying on the plane itself, all we need to do is solve this simultaneously. So the plane equations here I just label as pi. It's given as 2x plus by plus cz equal to 1, whereby the equations for line L is given as such. I can write in a compressed form, which is 2t, 2 minus a t, and then -1, -2t. And then all its x component, y component, and z component must satisfy the plane equation because it's on the plane itself. Okay. So by solving this simultaneously, I will have 2t plus b. My y is 2 minus t here, and then my z is -1, -2t, and then that must yield a 1 in this case. So I have 8, 4t plus 2b minus bt minus a c minus a 2ct equal to a 1. So from here, I'm going to collect, group all the constants together, and then group all the coefficients. So I group all the term that has t. Okay, so in this case, I have 8 plus 2b minus c. These are all the constant term. And then I have the term with the t. Now that will be a 4 minus a b, and then minus 2c t equal to a 1. Alright, now those are the one that we have currently. Okay, and then now all I need to do is just solve this simultaneously because there are only 2 variables involved. We notice that by comparison, constant must be equal to 1, and then the coefficients for t must be equal to 0. Therefore, I would have 2b minus c equal to -7. That's my first equation. Then my second equation will be b plus 2c must be equal to a 4 here. So all I need to do is just solve this simultaneously. Okay, now for instance, let me see how do I solve this. Okay, hold on for a while, just let me figure this out. So you're going to solve 1 and 2. Okay, so 2b there. Yes. And then that will be 14, 18. So 18 with the 5c. 18 with the 5c. Okay, so this is 5c should be equal to so 5c should be equal to 8 8 minus 14, so 14, 8 plus 14, 22. This is 8, so 2 here, 2, 4, 2, 8. Oh no, this is a 2, sorry. So we have a 2 here, so therefore you have C first. So I'm supposed to solve for B first before that. You can solve it by eliminations or substitutions. Okay, so let me see one more time. That will be a 5b, and then that is a negative 14. Add up with this negative 14, so there's negative 10. B will be equal to negative 2. B will be negative 2. And then for that, our A will be, because B is negative 2, and then our C will be a 3. Our C will be a 3. Okay, why do I write A then? Since I say it's a C, so C will be a 3. And then there you have it. We managed to solve all the values for B and C. Right. I hope that's clear. Okay. Now, next for second question. The P has a position vector as given as such. It's a 0, 2, 4. I think if you refer to my previous sections, I think I wrote it down wrongly. It's 204. It's supposed to be 0, 2, 4 here. Alright. Now our objective here is to prove that the perpendicular distance between P and the line is given as cert 5 here. Right. Now first of all, to work this out, we have to obtain a position vector on the line which is perpendicular to P here. Right. So for that, we're going to write the compressed form for this. The compressed form for R can be written as 4 plus 2t, 2 minus t, negative 1, negative 2t. Did I get it correct? Yeah, correct. Now from here, we can state that any point on the line can be given by this particular vector t. Right. So that will be our OQ. And then next we're going to work out the relative vectors for PQ. So relative vector for PQ, which is OQ minus OP, just for reference. So OQ minus OP, that will be 4 plus 2t, and then negative t here, okay, because subtract off, and then this one will be negative 5, negative 2t, and then that will be our vector or relative positions PQ. Now, knowing that PQ is perpendicular to the line, we can conclude that the vector PQ scalar product with its direction to line L must be equal to 0. Therefore, dot product with the direction must be equal to 0. And then let's give it a try here. Let's see what we have. 8 plus 4t plus a t plus a 10 plus a 4t must be equal to 0 here. So let's see what we have here. We have 5t. Did I get it right? Everything negative 1. Is it correct? Yeah, correct. Okay, so from here I will have 9t equal to negative 18. Therefore, the t will be negative 2. Now, knowing that the t is negative 2, I will be able to finalize my relative vectors PQ here. So I'm just going to write it down directly from here. Now that will be a 0 in this case, that will be a 2, and then that will be a 4, negative 1. Now that will be the relative vectors for PQ. If we wish to find the shortest distance between P to the line Q, or the perpendicular distance between P and the line Q, that can be obtained by evaluating the magnitude of the relative vector PQ here. And then this is given as 0 square plus 2 square plus negative 1 square square root, and then that directly yield cert 5, and then that conclude our proof then. I hope this would be useful for your learning. If you like what you are looking at, give it a thumbs up or subscribe or click the notification bell so that you can receive the most latest videos. Right? Thank you very much for watching. See